Okay, Lecture 5, Part 2, Erosion. Let's get into it. So in the last lecture video, we learned that erosion is simply the transport component of weathering and erosion, and this mainly occurs through running waterways and wind. There can be a large range behind that force, whether that's a tornado or a mild breeze, or a little creek in your backyard, or the Mississippi River. So out of all of these mechanisms, the most common agent of erosion is running water, that being in the form of rivers and streams. And when we combine the greater forces of water and wind and then throw that on top of a high elevation, then gravity will assist that process in producing something called mass wasting. This is a product of all of those things converging and essentially moving out massive portions of sediment and water, mud. This is how we get very dangerous mud flows not linked to volcanic activity. To talk about erosion, we have to first talk about at least superficially surface water hydrology. Simply put, that's how does water move about the surface and the near surface. So starting with precipitation, well, what happens as soon as it hits the ground? Number one, some of it will evaporate right away or start to evaporate. Another portion may be absorbed into the ground, and the rest will be runoff. And this runoff versus absorption is dependent on what type of substrate we are dealing with or what is at the surface. For example, if it rains in a paved parking lot or you pour your coffee out on the pavement in the parking lot, it's going to run off of the surface of that because concrete or pavement is not all that porous. So that's why you'll still have a pool, or, if you're in a parking lot and you have an oil leak in your truck or car or whatever, you'll see a trail of that left on the surface of the parking lot. If you are doing the exact same thing, dumping out your coffee cup on the dirt road leading up to your house, is it going to run off and pool in the same way? No, some of it's going to absorb into the ground. If you have a really clay-rich driveway or you've lined it with gravel, it may drain differently between those two options. If it's on gravel, it'll absorb much more quickly because there's greater pore space between those grains. And if you have something clay-rich, it might do a little bit of pooling, but after a few seconds, you should start to see it seep down into the subsurface. So in cities, we have a lot of runoff, which is why we require drainage and drain ditches within our cities and urban areas, whereas you don't see those nearly as often in rural areas because we don't need them. There's not nearly as much paved surface, so there's not nearly as much runoff. And there are a few other things that will still affect the amount of runoff that you will get in an area. So let's continue with our rural farmhouse example. If the ground is already saturated, say it's been raining on and off for several days, and suddenly we get a downpour, we are more likely to have runoff and flooding if that ground is already saturated, rather than if it's been dry for a very long time and then we get that downpour. And that's because the ground is already saturated. Those pore spaces between the grains are already filled with water, so it's more difficult for it to absorb water and bring more water into that. Whereas if it's in dry conditions, if it's really dry, then it'll absorb that water like a sponge and will have very little runoff. So the higher the saturation of that soil, the more runoff we'll have. Vegetation, plants like water, plants uptake water, so the more vegetation there is in an area, the less runoff there will be because it's absorbing more of the water. A rainforest will have less runoff than will the desert, given the same amount of water with the same starting saturation of the soil. So when we're talking about saturation and vegetation, what we're really talking about is the effect that those factors have on the absorbency of the subsurface or the soil. The third large factor in this is the slope or the gradient of the land. And that simply means that if there is a really steep slope where it's raining on top of a mountain, we're much more likely to have a great amount of rainfall along that mountain slope than if it were to just hit a very flat level parking lot. And that's because gravity is simply going to carry it from that high to a low. If there's not much difference between the high and the low, say in the flat paved level parking lot, then we're not going to see much runoff at all. It'll just sit there. And given that water always flows from high to low due to the force of gravity, runoff will eventually find its way to some sort of channel or low topographic point where that water will accumulate and continue to flow downhill given its path of least resistance. And as it starts to carve away this channel, as it accumulates in a low, this process will continue through time, and as the process continues, the channel will get deeper and deeper and deeper. As it gets deeper, it can accommodate more water because the volume is increasing of that channel, and the process just continues to amplify itself throughout time. The larger amount of water this can accommodate, the larger it becomes itself, so we go from a channel to a stream to eventually a river. So here we have a map displaying all of the major river systems within the continental US. Now note the areas colored in red are those which are the highest above sea level. Those in the mild tan brown color are about a medium height above sea level, and those that are green are at the lowest elevations, still slightly above sea level but not by much. And then in some very slight places where you see that dark green, almost black coloration, that's where it's below sea level. So Houston, Texas would be one example of an area that is below sea level, as well as New Orleans and a couple of other places. And why this matters again is because water will always flow from a higher elevation to a lower elevation. And a couple major river systems stand out here. So this may strike you. This is the Mississippi River, and then this here is the Rio Grande, meaning big river. Now, how do these rivers even get to be so large? Well, it's the same idea as what we just considered with the small channel. They started as just a small channel or a creek, and then eventually developed into streams and rivers slowly over the course of a long geologic period of time. And now the Mississippi River is actually, as a result, the main drain of the United States. You guys may have heard the word watershed before, and really what a watershed is a specific type or a specific area where all drainage leads to the same point. So it's any encompassing area with a common drainage point. Now we can have sub-watersheds and mild and smaller watersheds that we use for drinking water purposes, but we also have our major watersheds, such as the drainage basin of the Mississippi River. And you can see that this stretches over 31 different states. Several other major rivers, such as the Missouri River, the Arkansas River, Ohio, all lead into the Mississippi River, which eventually drains out into the Gulf of Mexico. Why? Because we are going from higher elevations out here to the low elevation. Water is moving from high to low due to the force of gravity. So what does this have to do with erosion, weathering and erosion anyways? Well, because we have so many rivers moving into one place and draining out of the same area, we actually have a great deal of erosion occurring along these paths. This is carrying a massive amount of sediment and discharging almost all of that into one singular spot. And this discharge point gives us a delta, which is where the mouth of a river meets the ocean. We'll get a little bit deeper into that idea momentarily. Now, all of the sediment that is carried in these rivers and streams is carried in one of three ways, all of which occur together. Number one, they can be dissolved in the water, so this would be referred to as in solution. They can be suspended in the water. This is going to be the lighter sized particles, so the clays, the silts, and maybe some fine sands, ones that are light enough for a stream to carry them, depending on how fast the stream is flowing, how much energy is in that system. And then lastly, the bed load. These are the larger, heavier particles such as pebbles, cobbles, and sometimes even boulders, again, depending on the energy of the system, that are simply shoved along the bed of the river or stream. They're pushed by slow rolling, sometimes even bouncing or dragging along that stream bed. Hence the name bed load. It's the load on the bed of the river. Here you can see a good visual of that. Again, water is flowing from a high point to a low point where we have our smallest particles, silts and clay, suspended at the top, some sand and maybe some larger silts and clays moving and suspended in the bottom. And then at the very bottom, right along the bed of the stream or the river, we have these larger particles rolling or sliding, grinding along that bed. And we know from the weathering lecture that we can expect some breakdown or weathering from that abrasive nature of those gravels and pebbles moving along the bottom of the riverbed. So the amount of sediment and the sediment size that are carried by a river or stream are dependent on the level of energy in that system or in that stream. How fast is it moving? What's the velocity of the water? And things that are going to affect the velocity of that water are, number one, the gradient or the slope of the stream. So is it moving from a very high to a very low, or just a slight high to a slight low? The steeper the slope, the greater the velocity of the stream. Discharge, so what is the actual volume of the water? A small creek will move an awful lot slower than a large river given the same conditions otherwise. And then the stream channel shape. If you try to visualize cutting a river right across and then looking at a side view of that, you might see something like this. And with this idea, our river is flowing relatively straight. There's some uneven edges, but the water movement is fairly well in a straight direction, which means that water would be flowing out of the screen towards us in our cross section. And water would actually be moving fastest near the deeper center of this section rather than along the sides, and that's because it doesn't have the same level of friction as it does when it's in contact with the ground. The same idea is illustrated here from our bird's eye view. So the longer the arrow, the faster the velocity of the water. We'll have faster velocities towards the center of the stream than towards the edge of the stream or the river. And you guys can test this out on your own too. If you next time you're at a river, take a look at the leaves floating down the center of the river rather than the leaves at the edge, and think about which one's moving faster. It should be the one in the center, right? For those of you who spend time outdoors, how often do you actually see a straight river? At least for an extended period, or like an extended distance. Not very often. Rivers like to bend, and that's because of the natural topography of the land. If it's completely flat, you might get a straight river, but here in Michigan, we've got a lot of hills, and our rivers like to bend. We call this a meandering river because the river is meandering back and forth. All this is the river trying to follow the path of least resistance and move along those topographic lows. So if you take a look at the topography of a land and the river that's going through it, you should see the river moving around the higher points. So the river will bend around the hills. And that's just because you're not going to see a river flowing uphill. Now, when we consider the bend of a river, our cross-section begins to look a little different. Because now instead of a completely straight river, we have an inner tighter curve and an outer wider curve. We end up with a cross-section looking like this, which means that we have less depth on this side and more depth on this side. And we will have, in turn, more friction on this side than we do on this side, which now means that the fastest water will be moving towards this half of the river. So back over here, we have a shorter arrow on the tighter bend and a longer arrow on the outer bend. So this is indicating the fastest path of the water motion. That's because it's going to be the deepest on that side. Where water moves fastest is where it can pick up the most sediment, or the heavier sediments. So along this outer edge where we have the fastest moving water is where we will get erosion. It will be picking up and carrying away those sediments. And then on the opposite side where we have slower moving waters, where we may have some deposition because it's going from a higher velocity along the straighter portion to slowing down, which means it can no longer carry those heavier sediments that it has suspended and will drop those out of solution, depositing some sediments along this side, which continue to make this more and more shallow. And this side, because it's cutting away, will continue to become deeper and deeper, and eventually this whole bend in the river itself will start to move this way as this continues to cut and this continues to build. So we'll be moving in this direction to the right. Another important note, in those high energy systems where the velocity of the water is highest, it not only is carrying larger sediment, but it's also carrying more sediment, period, of any size. Alright, don't let this graph scare you. All this is conveying is what we've been talking about up to this point. So if we take a look at the y-axis, we have the particle diameter. So we have increasing particle size or grain size from clay and silt, the smaller ones, all the way up to cobbles and boulders, the much larger ones. And on the x-axis, we have increasing stream velocity. In between these two factors, they have a mostly linear relationship, meaning that is a even, unchanging slope for the most part until we get up to the cobbles area. I'll touch on that in a minute, but what this really means is that there is an even ratio between the speed and the grain size, meaning, say, if I am moving at 1 meter per second is my velocity, then I should be able to pick up 1 pound of sediment. If I'm moving at 2 meters per second, I should be able to pick up 2 pounds of sediment. 3 meters per second, 3 pounds of sediment. These are just arbitrary numbers, but the point is it's 1 to 1, 2 to 2, 3 to 3, which is really all 1 to 1, giving this linear slope up until we get to cobbles and boulders. And the only reason that that changes is because we would need an awful lot more speed to move a boulder. There's a much bigger jump from the weight of a pebble to a boulder than there is from a silt from a silt to a pebble. So up here with the cobbles and boulders, we now have a much steeper slope, which means we have a much greater ratio of the velocity to the sediment size or sediment weight, meaning we would need something much faster to move something of this size. Okay, so this is a good point to hit the pause button and take a quick brain break if you'd like one. Feel free to tell me in the essay portion of your quiz if these points where I put in these pauses are actually helpful to you. If you are just find yourself skipping over these, then let me know and I won't throw them in anymore, but if you do find them useful, please let me know. So as channels develop into streams and rivers, they will continue to dig and carve out those paths that they've taken deeper and deeper. This eventually gives us what we refer to as the young stage of stream development or river development, giving us a V-shaped valley, meaning that the ground that it's cutting away, if we take a cross-section of it, we will end up with a V-shaped divot in that cross-section. With this stage, we can sometimes get rapids or babbling brooks or waterfalls because it has done so much cutting away that there are some significant enough jumps in topography within that stream bed that we can have localized increase in water velocity or waterfalls or rapids, in other words. There's no floodplain at this level, and we generally see something like this digging its way in between two large hills or mountains. So most all waterfalls initially start as rapids in rivers, and this is like what I was saying with a localized increase in water velocity, and that's because its velocity is slowing down as it encounters a large boulder. Right as it hits that boulder, that's slowing it down and almost making it stop, and that water will move along the edge of that boulder until it curves around to the front, where it will speed back up and will have a faster velocity. That faster velocity will then break down the rock that's right in front of it, or the bed of the river, and slowly carve away at it, at the softer, saturated sediment below, until we end up with a large enough cliff or drop to get a waterfall. Moving into the mature stage of a stream or river development, this is where we start to get a greater lateral erosion. This means that instead of so much digging deeper and deeper into the channel, it's reached the point where the sediment is not so soft and we're getting into what's been compacted and cemented. It's much harder to carve away, yet we still have the same amount of input of water, so this now is carving out in the horizontal direction more so than it is previously in the vertical direction. So it's not so much getting deeper as it is now getting wider. And this widening of that river is what gives us a floodplain. That is the area immediately around a river or stream, is shown in this like puke green color on the side of the river. And a good way to think about this is that if it were to flood, how high would the water rise and how much ground would it cover? So if we had this regular river and it suddenly flooded, we would see that it would now be this high, except that's not the actual width of the river, that's just under flood conditions. And so this would actually, at flood conditions, we might look at this at the bird's eye view and say that's a very wide river, but if we took a cross section of it, we would see that there's maybe only a few inches of water up to this point where it drops and there's several feet of water, picks back up, and then again only a few inches of water picking back up on the other side. Also in this stage, the meanders of a river, or the bends, start to become more pronounced as it's had more time to carve out and follow the natural shape of the land. And the slope of the river itself decreases, so we're moving away from that sharp V shape to more of a gentle U shape. Back onto the meandering, deposition and erosion within a river. We actually have names for those areas where we have the deposition at the slower moving velocities and the erosion at the higher moving velocities. And we've touched on this a little while ago in one of our previous lectures, but the inside curve where we have the deposition and the slower velocities is called a point bar. I had a classmate when I was an undergrad who liked to remember this one by saying that he had left his apartment deposit at the bar, so deposition at the point bar. And then we refer to the outside curve as the cut bank. And that one's easy to remember because that erosion and that weathering and erosion, that high velocity, is literally cutting away the earth. And sometimes in older, more mature rivers, you can actually see this. It's where you'll see something like this along the edge. That's how you know you're at the cut bank. And then you can see it pretty well in this image as well, where we have the point bar. You can see where the river actually once started. And this is from about here to here, all of the sediment that's been deposited along that point bar. And on the opposite side, from about here to here, is all that's been cut away. So eventually, this river will entirely move to the left, bottom left corner of the screen in this idea, and it's already moved quite a ways in that direction. So let's do a quick test on what we've gathered so far. Take points A, B, and C circled in red in this figure. If we wanted to get a cross-section of this, what might it look like? Option 1, 2, 3, or 4. Give you a second to think about it. Yep, so this would be option 3, and that's because we have the inner curve on the left, so that's going to be our point bar where things are moving slower, and we have deposition occurring, so it will be shallower on that side. What about the same for D, E, F? Another second to think about that. Yep, it's the exact opposite. So now we've meandered and we've switched directions in that S curve of the meandering river, so we would have the exact opposite of what we saw for points A, B, and C. Now, what about that area circled in blue along the straight bend of the river? Yep, nothing exciting, just fairly even all the way across. As a river continues to age and we move into the older stages, what we tend to see is a very wide floodplain because it can't move too much deeper vertically. It can only keep moving out laterally or increasing its width given the same amount of volume. And as it's continued to meander around these surfaces, eventually it's worked up a flatter area, which also means that we can have a wider floodplain. Eventually, the bends in the river will become so tight that we will end up with what's called an oxbow lake. As you can see in this example, this is a very mature, older river where we have some pretty exaggerated bends. And then at this spot right here, we've got a meandering river that almost comes back and converges on itself. This is the stage right before the formation of an oxbow lake. Because of the quite literal meandering of all rivers, that deposition and erosion relationship that causes local portions of the river to shift in any one direction, wherever in the direction of wherever it is cutting, or the cut bank. Eventually we'll get where those two rivers will meet each other, or those two portions of the river will meet with each other and collide, and once they meet with each other, they will close off this portion, and the river now has a new path of least resistance where it will straighten out and leave behind the old bend. And this resulting old bend is called an oxbow lake. Here's an example of a real oxbow lake where this river originally moved this way and curved around like so, and then back out this direction, but these met each other at some point, and then the river had a new path of least resistance to flow, so it started to move straight, and we have this old bend of the river left over, which is now a lake, specifically an oxbow lake. And just to clarify what I mean by now has a new path of least resistance, if this river is moving up and around this direction, that's a much longer path, and it's quite out of the way than when these two meet up with each other, when it can start to just go right through here. That's a much shorter path. So instead of doing one of these all the way around, as soon as these meet each other, it will go this way instead of going all the way up and around. It's just a shorter distance, less work. Okay, so quick review of what we went over in the weathering section. Because weathering and erosion go hand in hand, we often see weathering occurring during the erosion stage. So as things are being transported, they are likely to be more broken down. The further something is transported, the more weathered it is and the more erosion it's undergone. So sediments that are further away from their source are likely to be more well-rounded because they've traveled further and they've been sanded down almost, or that abrasion has cut off their sharper edges, and it's likely been rolling in that fashion because things that are loosely spears will continue to roll, and as it rolls it will smooth over. So we can talk about rounding from poorly rounded to well-rounded, or something that's very angular to well-rounded, whole range in that world. Generally when we're talking about this, we talk about things in terms of its sphericity, or how round it is. So with that being said, out of these options A, B, C, and D, which one appears to have undergone more erosional transport? Yep, it's B, and that's simply because it has the most well-rounded grains. Everything else is fairly well angular. C is kind of rounded, but it's not. It's just not quite as rounded as the grains within sample B. What about sorting? Well, again, the more weathering and erosion that occurs, the more well-sorted a sediment will be. And that's because close to the source we may have a deposition of a range of sediment sizes, but as it's carried further and further in different energy level systems, it's likely that it will deposit out the similar sized particles. So take, for instance, the point bar of the meandering river. Because it's going along a straighter path and moving a bit faster, as it comes around that bend, it starts to slow down, and it will still hold up the lighter grains, the silts, and the clays, even at that speed, but the sands and the gravels that it may have previously been carrying around the straight portion, it now does not have the same energy level to carry those, so it will continue to carry the silts and clays, but it'll drop out the sands and gravels, so we would have a sediment at that point bar that is fairly well sorted because we've removed the smaller sediments, or more so we've removed the larger sediments, leaving those at the point bar while the smaller ones continue to be carried away. So then we have a fairly well sorted sample with grains that are similar in size. So depending on what the energy level is, we will have different grain size, but generally speaking, the more transport, the more erosion, the more weathering, the more well sorted, and the more well rounded. As promised, a little more on deltas. This is a rapid change in velocity. So a delta is where we have, again, all of the sediment that's carried in a large, deep river being poured out into the ocean. And the speed of that river is relatively high in comparison to that of the ocean. And the ocean's also likely flowing towards the land where the river is flowing towards the ocean, which means that as soon as they impact each other, they're going to very rapidly slow down, which results in almost all of the sediment immediately being dumped out. And this is what we see here at that delta, at that point where the mouth of the river, the end of the river, meets the ocean, and we have that immediate change in velocity or energy of the system. And this is essentially, so a delta is basically a large sediment dump, all of the continental sediment dump. And we have a lot of these spread out throughout the coastlines. At these deltas, we end up with alluvial fans. So the delta is where that river just meets the ocean. So that would be like right here or right here. And then we end up with an alluvial fan, which is the spreading out of all of that sediment. Now, the immediate collision between those two water bodies and that rapid change in energy, again, the heavier things will fall out first because the lighter things will still be suspended. And so while everything gets dumped out, it does have some gradation. All of the heavy things will end up closer to the mouth, and the lighter things will end up further away. So we have a natural gradation from the heavier things to the lighter things moving outward. And so that is our alluvial fan. It almost looks like a nice hand fan that you can, it makes that really satisfying noise when you like whip it open and begin to fan. And this is an older alluvial deposit, so this is where water used to be coming up to this point, where we had discharge of a river into a larger body of water. We can have this in very large lakes as well, but it's much more common in oceans and coastal areas. And on the note of coastal areas, we also get different types of erosion associated with those environments specifically. So this is erosion that is predominantly controlled by wave action, or in other words, a longshore current. So first, to understand that, we have to understand that the motion of the ocean is not so much a wave as it is a circle. This is why waves fall in on themselves, and surfers are able to glide through those tunnels. Those tunnels are circles, right? And that's because the motion of the waves are actually circles. It's just that they don't always break onto themselves because those cycles are being broken by the cycles next to them. This is also why a sine wave or a... Let's see, where was I? So that's why sine waves and cosine waves are related to circles. That's what a circle is if you lay it out on a graph. There's some better visuals and videos of that online, but this is why waves and circles go together, because that motion is actually a circle rather than an oscillation up and down. As waves move closer and closer to the shoreline, their wavelength begins to decrease, so they're getting tighter together. Notice a much longer wavelength from this trough to this trough than from this trough to this trough, or this trough to this trough. And then the wave height itself also increases. The further out you go into the ocean, the less choppy the waves are. That's why we have this surf zone or break zone towards the shoreline, where the waves are much choppier and they actually will break and collapse onto themselves, forming those nice tunnels that we like to surf through. And to just further highlight what I mean by the motion of the ocean is actually circles rather than waves, is that if we were to follow a singular water particle from out here towards the shore, it would not move simply up and down in a wave, but it would rather move in a circle along the curve towards the shoreline. It's because the ocean is effectively stirring. When you look at the surface of the ocean, you're not watching the exact same water just bounce up and down along the surface, but rather you're seeing new particles emerge and submerge each time. So the Longshore Current actually carries this same idea. The Longshore Current is the direction that the water flows along the shoreline. This is where the waves come in contact with the shore, and they're refracted or bent in the shallow water, meaning that they are forced to move in that direction. So this means that if we were to follow those that same water particle or molecule, as soon as it actually gets in contact with the shore, it's no longer moving in that circular motion, but rather the current on whole itself. The water molecules are still moving in the circular motions, but now the current, instead of moving in a wave, is moving in a zigzag. So hopefully this better highlights it, and that's because the waves are crashing and then subsiding and crashing and then subsiding and crashing and subsiding, but they're doing this overall in a direction along the shore. So that longshore current is that overall direction. Even if that zigzag pattern goes back and forth, it's still overall moving in one direction. So here's an example of where we can actually see longshore drift in action. Next time you guys are on a plane on a clear day and you're flying over a coastal area, maybe you've got grandparents in Florida like everybody and their mom does. I know I do, so what I like to do is look out the plane window and try and figure out what direction the longshore current is flowing or which way the water is moving. So in this particular case, it is useful for us to look at the boardwalks. That's what these long straits are that are pointing out. This is a very populated area. People want to go out into the ocean, so we have boardwalks for fishing and walking and sunset walks along the beach, so on and so forth. So because the longshore is moving in this direction, what we end up with is a buildup and blockage of sediment along this side of the boardwalks. That's why you see that same pattern repeated along all of them in this direction. So in this case, we see that buildup on the north side because the longshore drift is flowing southward. Which means that erosion is occurring in what direction? Southward. Which means the sediment is moving from this side to this side. And that just scratches the surface of water-based erosion. When we talk about wind erosion, we're usually talking about lighter sediments just because wind can't move things nearly as much as water can for the most part, unless we're talking about high-speed winds such as tornadoes and hurricanes, but streams and rivers are far more common and continual in action than tornadoes and hurricanes. And so this is in areas where we have either arid regions or along ocean coastlines, because we tend to have higher winds along those coastlines. So though it's a small area relatively, maybe not more than 200 to 300 feet inland from a coastline, we can still get similar wind erosion in ocean coastlines or even some of the Great Lakes coastlines as we do in actual arid regions such as deserts out west. Within this, there are two main types of wind erosion. Number one is deflation. This deflates or lowers the land. So it's mainly just cutting away and moving sediment from one spot to another. And then we can have number two is sandblasting, which is it's so strong that it is slowly cutting away at existing rock and continuing to pick up more sediment. So that's again where weathering and erosion overlap, but the sandblasting occurs because there's already sand or abrasion or suspended sediment, that's usually sand, suspended in the air, which is slowly cutting away at existing rock. Sandblasting is also something that we can do in industrial settings. One example would be if perhaps you live in an older antique home. These are really common in Kalamazoo, where we have homes that are from the late 1800s to early 1900s that have since been converted into multi-unit apartment buildings. They may have antique air grates or air duct covers that have very ornate moving metallic designs that, of course, a landlord has painted over about 12.5 times in different shades without paying any attention to the screws or hardware otherwise. And so if you were wanting to restore that, you might take those covers off and take them to a place that does sandblasting, which is where they have an air compressor that will shoot out very fast moving air, somewhere between I think like 140 to 200 miles per hour. That has a bunch of well sorted and well rounded fine-grained sand in it, made of quartz, because quartz is hard enough to actually be able to carve away at that, which will take away all of the relatively soft paint, but leave the hard metal below, giving a nice new surface to polish and put back into your antique restored home. Where we have sandblasting in nature, however, it does not move nearly that fast. We have to really put some power behind it to get it to do something like restoring your antique air grates. In nature, wind can only lift it so high. Usually this is at max about 1 meter or 3-ish feet, which results in formations called mushroom rocks, which is where we can see something like this, where the wind erosion is clearly seen at the maximum being about this point. That's as high as the wind could carry those sediments with the level of energy that it had before it dropped them out, or it dropped just further back down into the portion or depth that it could carry it, which leaves this heavier, wider chunk up top and this thinner support on the bottom that kind of looks like a mushroom, hence the mushroom rock. These low-moving winds don't always form the mushroom rocks, but sometimes we'll just carve off a side of a rock, making it a flat, frosted side. Frosted, we call it because it's just been smoothed or polished naturally. So this rock probably had a rounded edge that came out to almost where its shadow is in this picture. But through wind erosion, sandblasting, and abrasion, has been carved and smoothed into this flat surface on this side. Okay, so this is again another good point to stop before we get back into things. We've got about 10-ish or so minutes left of this lecture, and so I'll give you a chance to put it on pause if you'd like to do so. And I've already got the answer up there for you on this one, and that's because you should know what the answer is right away. What caused this mushroom rock that you see in this picture? Yep, it was wind erosion. Something specific to us Michiganders is the wind erosion, which has built our beautiful sand dunes. Within our sand dunes, we actually have a series of layers. So every sand dune starts off as just a simple tiny hill, and as the wind is moving in the direction, sediment will continue to pile up until it can't hold that or suspend that in place any longer, which it will collapse and fall towards the ground in that direction, and a new layer will start to build up until it gets to the point where it can't hold it at that point anymore, and again it collapses, and eventually we get several layers of this. It builds up over time, and this is how we can actually tell what direction the wind has been flowing throughout the construction of this sand dune. So in this case, it's pretty clear that the wind was moving in this direction because that's in the direction that it is collapsing, or the side with the slip face. A lot of times though, if we were to actually cut through any number of sand dunes that we see on Michigan, we would see that the direction of the wind has changed quite a few times. And so these lineations or marks of where there has been collapse and those new layers have added on. This formation is called a crossbed. We will get into that more in the sedimentary structures lecture. So we can see this crossbedding that in real time or in real life, when we were to cut through a sand dune, we would see that they would be heading in this direction for a little while, and then they'd switch it up and head the other direction. And so in that, we can sort of read into the past and tell when a predominant wind direction has changed, which allows us to make other inferences about climate at different periods of time. And how local wind conditions have changed in response to different weather conditions. So we tend to have, for example, more rapid switch-ups or more frequent changes in wind direction associated with higher storm environments. And more storms are also associated with warmer climates, and that's because in warmer climates there's more condensation and more evaporation and more precipitation. So all of these things connect with each other, and we can actually read a lot from looking into sediment and rocks about what our Earth's past has looked like. So that's all I have for you guys. We didn't quite make it to the 10 minutes, so maybe that was a good pause or not. But anyways, you have the Lecture 5 quiz to take. If you haven't already done so, go ahead and finalize your lab. Make sure that that's ready to go and turn in. And then I want to keep things pretty mild and easy this week, but I also want to keep your midterm on your radar. That's only a couple weeks away. I will be putting together a study guide for you guys, but if there's anything that you've been unclear on any of the previous lectures, start putting that on the back burner and you know, pop the question next time we're in class. And if you're thinking that you have a question on it, the chances that somebody else is thinking they have a question on it are likely very high. So you guys have a good weekend, and I will see you next time.